Hello everyone and welcome to my lecture on resonance part 2. Here we will mainly discuss about certain important points which you should keep in mind while drawing and finding the stability of the resonance structure. The first point that you should remember is while drawing the resonance structure we use a curved arrows. The curved arrows always indicates the flow of electrons. The tail of the curved arrow indicates the position from which the electron is moving, and the head of the arrow indicates the position to which the electron is moving. These curved arrows should move in one direction. For example, this is a pi electron system which is in conjugation with the lone pair electrons. So, the lone pair electrons is donated, the central carbon atom becomes pentavalent, and so this carbon atom becomes pentavalent as soon as this lone pair is donated, and carbon can't be pentavalent, so immediately this double bond breaks and electron comes on this carbon atom. But many a times you represent it like this, where both the curved arrows are moving in an opposite direction. One this way and other one in the other way. This is not the correct way of representation. Electrons should flow in one direction. The third point is the molecules cannot be represented by a single structure. The molecules that cannot be represented by a single structure are shown by a combination of two or more canonical structures, and those canonical structures are linked by a double-headed or a double-headed arrows, and that is how we draw the canonical structures. The fourth point that you should remember is the number of pi paired electrons and the position of the constituent atoms relative to each other should remain the same in all canonical structure. The total number of paired electron and the position of the constituent atom relative to each other should remain the same in all canonical structure. Just see that this is the first one is a alpha beta unsaturated ketone. Here all the canonical structures are having the same number of electrons, and the position of all the atoms remains the same in all canonical structure. Look at the second molecule, where the double bond is in conjugation with the lone pair of electrons. Here also the number of paired electrons remain the same in all canonical structure, and the position of the atom doesn't change in any of the canonical structure. Similarly, here are other examples where you can see that the number of paired electron and the position of the atoms in relative to each other remains the same in all canonical structure. So this is very important, that the number of paired electron and position of the constituent atom relative to each other should remain same in all canonical structures. This is the difference between resonance and tautomerism. It should be noted that if the starting compound is a neutral species, all canonical structures should be neutral, or net charge on the canonical structure should be 0. Similarly, if the starting compound is positive, the net charge on all canonical structure should be positive, and if the starting compound is negative, the net charge on all the canonical structure should be negative. Look at these examples. When we started with a neutral compound, the canonical structure, though it has a positive and a negative charge, but this positive charge is nullified by the negative charge and the net charge on the compound is 0. Similarly, in this canonical structure also the net charge is 0. So we started with a neutral compound, and in all the canonical structure the net charge is 0. Look at the second compound. The second compound is also a neutral compound, and in the canonical structure there is separation of charge, but the net charge on the compound is 0. But look at this compound. We have started with a positively charged species, and the canonical structure is also having a positive charge. Here we started with a negatively charged species, and the canonical structure is also having a negative charge. So therefore, while drawing the resonance structure, you should always remember that if we start with a neutral compound, the all canonical structure should be neutral. If you start with a positively charged compound, all canonical structure should be positive. If you start with a negatively charged species, all the canonical structure should have a negative charge. The next important point is the stabilizing effect is more when all the canonical structures have same energy. Look at this example. This is acetate ion, CH3CO-. This negative charge, this excess negative charge on the oxygen is in resonance with the pi electrons, and so in one of the canonical structure we have the double bond is shifted from this place to this place, and the the negative charge come on this oxygen now. But you see, in structure 1 or in structure 2 there is no major difference in the structure. The only difference is the double bond in structure 2 is shifted from here to here, negative charge is shifted from one oxygen to the other. So both the canonical structure is almost of the same energy. So when in a molecule the canonical structures have same energy, then the stabilizing effect is more. The more number of canonical structure, greater the delocalization of electron and more is the stability of the compound. If you draw the resonance structure of paranitrophenol and metanitrophenol, which I have given in as an assignment in my last video, you must have seen that paranitrophenol has more number of resonance structure than metanitrophenol, and therefore paranitrophenol is more stable than metanitrophenol. So the more number of resonance structure, greater the delocalization of electron and more is the stability of the compound. Canonical structure in which there is a greater separation between unlike charges usually have a higher energy content than those having less separation or no charge separation. Less stable canonical structure contributes less to the hybrid structure. Now, when we draw the resonance structure, all canonical structure or resonance structure do not contribute equally, do not always contribute. Sometimes it contributes, just like in this example, both the resonance structure contributes equally. But here you will see that both the resonance structure do not, in this example you will see that both the resonance structure do not contributes equally. One of the resonance structure in which the charge separation is more, that particular canonical structure contributes less, because it has a higher energy content and is less stable. Whereas the canonical structure where there is no separation of charge are more stable, and this particular canonical structure contributes more to the resonance hybrid structure. So here this is an example of formic acid. In formic acid, the lone pair electron on the oxygen is in conjugation with the pi electron of the carbonyl group, and so it can undergo resonance, and this is the resonance hybrid structure of formic acid. So, formic acid can be represented by this structure also, and also can be represented by this structure, but of course this structure contributes less to the hybrid structure because there is separation of charges, whereas in this structure there is no separation of charge. So, this structure will contribute more to the resonance hybrid structure. The next point which you should see, this is less stable and this is more stable. The next point which you should consider while drawing the resonance structure is that the structure in which the octet of every atom is complete is more stable canonical structure. Let's see an example. Yes, this is an example in which the positive charge on the carbon is in conjugation, can enter into resonance with the pi electrons on oxygen, lone pair electrons on oxygen. But when the lone pair electrons on the oxygen is donated, then we reach to this structure. This structure, these are the two canonical structure, but both structures do not contribute equally to the resonance hybrid structure. Which one do you think is more stable and which is less stable? The more stable structure contributes more to the resonance hybrid structure. Here what should we consider? In this resonance structure, see, this carbon is having a positive charge and therefore its octet is not complete. Whereas in this resonance structure, the octet is complete for all the atoms forming the bond, and therefore this canonical structure will be more stable in spite of oxygen having positive charge on it. So, the structure in which octet of every atom is complete is more stable canonical structure. This is a more stable canonical structure, because in this all the atoms that are making the bond are having octet complete. This carbon is having an octet complete, this oxygen is having octet complete, this carbon is also having octet complete. So this is a more stable structure. Canonical structure where the negative charge is on electronegative atom is more stable. This is the canonical structure for carbonate ion CO3 minus 2 carbonate, all of you know, sodium carbonate Na2CO3. So Na2CO3, so carbonate CO3 2 minus, and so carbonate can be represented by these resonance structures. So carbonate can have 3 resonance structures, but all resonance structures, are they contributing equally? No, they are not contributing equally. Let's see which is more stable. This is more stable because here there is no separation of charges, and so this is the most stable. In the remaining 2 structure there are separation of charges, but still this compound, this resonance structure is least stable, because oxygen, which is more electronegative, is having positive charge, and carbon is having less electronegative, is having negative charge. Whereas in this resonance structure, all the oxygens are having negative charge. Oxygen is more electronegative, it is having negative charge. So this structure is comparatively more stable than this structure. So this compound is more stable because there is no separation of charges. Okay, there is only negative charge on oxygen but no positive charge, so there is no separation of charges, and so this is the most stable structure. And then this is the next stable is this, because in this structure, though there is separation of charges, but oxygen is having negative charge, all the oxygen having negative charge. But this is a least stable structure because in this, one of the oxygen is having positive charge. The next point is, for proper delocalization of electrons, all the atoms taking part in resonance should be in the same plane. Look at this example. This is NN dimethyl aniline. Aniline is NH2, and in that both the hydrogen is substituted with the 2-methyl group, and so it becomes NN dimethyl aniline. In that you can see that the lone pair electron on the nitrogen can enter into resonance with the ring, and this lone pair electron can be in conjugation with the pi electrons of the ring. Why? Because this nitrogen and all the carbon atoms of the ring are in the same plane. Since they are in the same plane, therefore, the lone pair electron can enter into resonance with the ring. But what about this molecule? Here, the 2-methyl groups are not only present on the nitrogen, but in addition to that, there are 2 more methyl groups at the ortho position. And because of these 2 more methyl groups at the ortho position, this nitrogen atom goes out of plane to avoid the steric hindrance. This nitrogen atoms goes out of plane of the benzene ring. That means the benzene ring and the nitrogen atom is not in the same plane. The 6 carbon of the benzene ring and the nitrogen here is not in the same plane. Since the nitrogen and the carbon atoms of the benzene ring are not in the same plane, so though there is lone pair electron on nitrogen atom, this lone pair electron cannot enter into resonance with the pi electrons of the benzene ring. So the resonance here, you can see the arrows. Here the resonance is only between the pi electrons of the benzene ring, whereas here the resonance was between the lone pair electron on the nitrogen and the pi electrons of the benzene ring. Now this is the last point which you should remember. While drawing the canonical structure, one should keep in mind that each curved double-brabbed arrow indicates movement of 2 electrons. Each curved arrow indicates movement of 2 electrons. Therefore, a negatively charged center after giving 2 electrons, become neutral, and a positively charged center after gaining 2 electrons become neutral. A neutral center after gaining 2 electrons become negative, and a neutral center after giving 2 electrons become positive. Let us understand this with an example. This is the same example which we have done earlier, alpha beta unsaturated ketone. Now what has happened to this? The moment the oxygen pulls the electron towards itself, oxygen, which was a neutral center, gains 2 electrons and became negatively charged. The carbon adjacent to it, which is donating electron, becomes positively charged. See, the carbon becomes positively charged. Now what happens? This carbon, the moment this carbon becomes positive charge, it pulls the pi electron adjacent to it towards itself, and so the pi electron shifts here and the terminal carbon also becomes positively charged. What happens to the central carbon? What happens to this carbon? This carbon neither loses or gains electron, and so this center carbon remains neutral. So I hope you understood all these 12 points well. Once you understand all these 12 points better, you will be able to draw the resonance structures quickly. And that's all for today's lecture. Thank you for watching my videos. If you like my video, please subscribe and press the bell. Today again I want to end my lecture with a thought. The best view comes after the hardest climb. Thank you.